welcome to this explainer. Okay, today we're diving into CBSE Class 10 Trigonometry, and we're going to break the whole thing down right here on our virtual whiteboard. Look, if you're gearing up for your board exams, you already know how absolutely crucial this chapter is, right? It's literally the bridge between basic geometry and advanced calculus, and getting a solid grip on it, well, that's going to lock in a massive 7 to 10 marks for your final score. So we're going to build your conceptual clarity completely from the ground up today. The goal here isn't to just blindly memorize a bunch of formulas, but to genuinely understand the geometric logic behind them. Let's get into it. So here's our game plan for today. Section 1, welcome to trigonometry. 2, mastering the 6 ratios. 3, deriving standard angles. 4, the big 3 identities. 5, avoiding common exam mistakes. And finally, section 6, acing 5-mark questions. To kick things off, we really have to talk about the sheer weight of this chapter. 7 to 10 marks is huge. It can completely shift your grade. But honestly, beyond just the exam, trigonometry has this almost magical real-world utility. It lets us measure the physical world when walking up with a tape measure is literally impossible. Just imagine figuring out the exact height of the Qutb Minar just by standing on the ground and looking up at the peak, or, calculating your river's width while just standing on a balcony. And this isn't some new modern trick either. This traces all the way back to the legendary Indian mathematician Aryabhata. He introduced this concept called the half-chord, or ardaghya, which actually evolved over centuries of translation into the word we now know as sine. Pretty cool, right?
All right, moving into section 2, mastering the 6 ratios and building your right triangle framework.
Okay, imagine putting a magnifying glass on one specific acute angle inside a right-angled triangle. The big shift here is that we aren't just looking at the triangle's general shape anymore. Instead, we are building a highly precise mathematical bridge between that specific angle and the proportions of the triangle's sides. This is where we establish definitions for sine, cosine, tangent, cosecant, secant, and cotangent. Now, you already know the hypotenuse is always the longest side, the one directly across from the 90-degree angle. But the other two sides, the opposite and the adjacent, well, those depend entirely on which angle you're actually focusing on. And that brings us to this brilliant side swap concept. It proves that the identity of the opposite and adjacent sides will completely change depending on which corner of the triangle you happen to be standing in. Imagine you're physically standing at angle A. The side way across the triangle from you, that's your opposite. But if you walk on over to angle C, that very same side is suddenly right next to you, making it your adjacent side. It's all relative to your reference point. Which leads us perfectly into the invariance principle. I want you to think about this carefully. If your angle stays exactly the same, the ratio stays identical. It does not matter if you're measuring a tiny 2-inch diagram in your textbook or the actual massive Qutb Minar. We prove this using the AA, or angle-angle, similarity criterion. If you've got a small right triangle and a giant right triangle, and they share the exact same acute angle, their side lengths are perfectly proportional. So the trigonometric ratio is a unique property of the angle itself. The physical size of the triangle doesn't matter at all. On to section 3, deriving standard angle values. Let's see where the numbers in that famous table actually come from. We're definitely not just going to rote memorize a table today. We're going to logically derive exactly where those numbers come from, right here on the whiteboard. Let's map it out. Imagine drawing an isosceles right triangle. Because it's isosceles, the 2 acute angles have to be 45 degrees, and the 2 non-hypotenuse sides are perfectly equal. Let's just call them both A. Now plug that into the Pythagoras theorem. A squared plus A squared equals 2A squared. Take the square root of that, and boom, your hypotenuse is A root 2. So, if we want the sine of 45 degrees, we take the opposite side, A, and divide it by the hypotenuse, A root 2. The A's beautifully cancel out, leaving you with exactly 1 over root 2. No memorization required. Now what about 30 and 60 degrees? Well, if you take an equilateral triangle and slice it right down the middle, it instantly hands you all the geometric proof you need. Start with an equilateral triangle where every side is 2A. That means all angles are 60 degrees, right? Now drop an altitude straight down the middle. This perfectly chops the bottom side into 2 pieces of length A, and it splits that top 60-degree angle into 2 30-degree angles. Use Pythagoras again on this brand new right triangle, and your altitude works out to be A root 3. So look at that 30-degree angle at the top. The opposite side is A, the hypotenuse is 2A. A divided by 2A is exactly 1/2. Sine 30 is 1/2. It's just pure, satisfying geometric logic. Having derived the logic yourself, this cheat sheet table finally makes sense.
It becomes your ultimate one-page summary for completely crushing exercise 8.2 in your exams. Instead of staring at a bunch of random, scary-looking fractions, you actually know the backstory of every 1 over root 2 and root 3 over 2. They were forged from basic triangles. And hey, don't forget, tangent is literally just the sine value divided by the cosine value.
Section 4, the Big Three Identities. This is your essential algebraic toolkit. Derived straight from the Pythagoras theorem, these 3 statements are what we call your identity suite. They are the algebraic heavy lifters you'll need to simplify complex expressions. First up, sine squared a plus cosine squared a equals 1. That is your absolute anchor, valid for angles from 0 to 90 degrees inclusive. The other 2, linking tangent squared with secant squared and cotangent squared with cosecant squared, are what you'll constantly pull out of your toolbox for exercise 8.3. Just keep an eye on those specific angle constraints. Notice how the tangent identity is strictly less than 90 degrees? That's because tangent is actually mathematically undefined at exactly 90 degrees. All right, Section 5, avoiding common exam mistakes. Let's correct those high-pressure notation errors before they happen. There is a fatal yet incredibly common mistake students make under exam pressure, and it's treating sine A like an algebra multiplication problem, like sine times A. No way. You have to remember the symbol sine is completely meaningless on its own without its angle attached. It's a unified mathematical function describing a ratio. It is strictly tied to the perspective of angle A. Don't ever try to separate them. You also have to dodge what I like to call inverse confusion. You need to strictly separate the reciprocal relationships you're using right now from the advanced inverse functions you'll learn in higher grades. If you see sine A written entirely in brackets to the power of -1, that's just basic algebra. It just means 1 over sine A, which is a reciprocal, cosecant A. That is entirely different from the inverse sine function, which looks like the word sine with a little -1 superscript. Please, do not mix those up on exam day. Here's a great pro tip. You can actually mentally double-check your exam answers on the fly using physical limits. Think about it. Sine and cosine are calculated by dividing a side by the hypotenuse. And since the hypotenuse is undeniably the longest side of a right triangle, you are always dividing a smaller number by a bigger number. Because of that, the values of sine A and cosine A can literally never exceed 1. Conversely, their reciprocals, secant and cosecant, are always going to be greater than or equal to 1. So if you're rushing through a calculation and get a sine value of 1.5, well, you instantly know you've made a mistake and need to recount. Finally, Section 6, acing 5-mark questions. Let's talk about executing the perfect proof protocol. A really fantastic strategy for these long answers is to sprinkle your writing with NCERT-aligned, professional vocabulary. When you write out precise terms like trigonometric identity or correctly reference acute angles, it instantly signals to the examiner that you truly know your stuff. Fun fact, even the word cosine is rooted in complementary angle logic. It literally stems from the Latin cosinus, meaning the sine of the complement. Flexing this kind of theoretical grasp fundamentally elevates your entire exam paper. Okay, let's talk actual execution. If you stick to this rigid step marking protocol, you guarantee that every single logical thought gets you a fraction of a mark. Step 1, always write out the left-hand side, the LHS, clearly before you start moving things around. Step 2 is my favorite pro tip. If you're staring at a really complex fraction, try dividing the numerator and denominator by cosine theta or sine theta right out of the gate. This elegantly forces the whole expression into tangent and secant terms, which unlocks your entire identity suite. Step 3, explicitly write down the formula you're using in brackets on the right side of the page. Step 4, do not skip algebra steps in your head. Show every single transition. And Step 5, conclude proudly with the undeniable statement, therefore, LHS equals RHS, hence proved. You really have to remember that in CBSE board exams, the structural process is just as vital as getting the final solution. The examiners aren't just looking at the finish line, they are rewarding your logical synthesis and how cleanly you communicate your mathematical thinking. So as we wrap up this explainer, grab your notebook and ask yourself, which formula derivation are you going to conquer on your whiteboard right now? Are you going to slice an equilateral triangle to prove the 30-degree ratios? Or are you jumping straight into a gnarly 5-mark identity proof? Dive into the practice, trust the geometric logic we just built, and you will absolutely ace this chapter. Happy calculating!